14 billion years ago, something impossible happened. Every atom in your body, every star in the sky, every galaxy we can see, all exploded from a point smaller than the period at the end of this sentence. But here's what will blow your mind. The Big Bang might not be the beginning at all. We're about to explore colliding dimensions that birth universes, black holes that contain entire realities, and quantum loops that make time itself bounce backwards. If you're ready to discover what really came before everything, hit that like button and subscribe, because this journey will change how you see existence itself. Prepare yourselves. We begin. Music, picture this. You're trying to divide by 0 on a calculator, and it just says error. That's exactly what happens when physicists try to understand the very first moment of the Big Bang. We call it the singularity problem, and it's been driving scientists crazy for decades. According to our best theories, if you rewind the universe like a movie playing backwards, everything gets smaller and smaller until it reaches a point of infinite density and infinite temperature. That's the singularity. But here's the thing that keeps physicists awake at night. Infinite anything in physics usually means your math has broken down completely. Think of it like trying to cram every person on Earth into a space the size of a pinhead. It doesn't work. The laws of physics we know and love simply stop making sense when you reach these extreme conditions. Einstein's general relativity, which beautifully describes gravity in space and time, starts throwing up its hands and saying, "I quit." What makes this even more mind-bending is that this isn't just about the beginning of matter and energy. This is about the beginning of space itself. Before the singularity, there wasn't even emptiness. There was literally nothing for anything to exist in. No up, no down, no here, no there. The temperature at this moment would have been 10 million trillion degrees. That's hot enough to make the core of the sun look like an ice cube. At these temperatures, not only would atoms not exist, but even the fundamental particles that make up atoms would be torn apart into pure energy. But here's where it gets really weird. If the singularity actually happened the way our equations suggest, then asking what came before it is like asking what's north of the North Pole. The question itself might not make sense, because time itself supposedly began at that moment. This is why brilliant minds have been working overtime to find alternatives. Maybe the universe didn't actually reach infinite density. Maybe something else was happening that our current theories can't capture. Maybe the Big Bang wasn't really the beginning at all, but just a transition from something that came before. Recent discoveries are pointing toward exactly that possibility. Advanced telescopes are picking up patterns in the cosmic microwave background radiation that suggests the universe might have had a complex history before the Big Bang. These aren't just theoretical ideas anymore. We're starting to see actual evidence. The singularity problem isn't just a mathematical headache. It's a doorway, and scientists are finally figuring out how to walk through it. But to understand what might have come before, we need to dive into the strangest realm of physics, where space and time themselves become choppy and uncertain. Welcome to the smallest possible scale of reality, where everything you think you know about space and time falls apart. At distances smaller than 10 to 35 m, space isn't smooth like we imagine. It's bubbling and churning like a pot of boiling water. Scientists call this the quantum foam, and it's where the rules of everyday reality go completely haywire. Imagine zooming into the surface of a calm lake. From far away, it looks perfectly flat. Get closer, and you see gentle waves. Closer still, and you notice tiny ripples. But keep zooming into the molecular level, and suddenly the smooth surface becomes a chaotic dance of individual water molecules bouncing around frantically. That's what happens when you zoom into the fabric of space itself. At the quantum foam level, pairs of particles spontaneously pop into existence and then annihilate each other in less than 10 to the minus 43 seconds. That's so fast that light, the fastest thing in the universe, can only travel about 10 to the minus 35 meters in that time. We're talking about distances so small that if you enlarged an atom to the size of the solar system, the quantum foam would still be smaller than a grain of sand. This isn't science fiction speculation. We've actually measured this foam indirectly through something called the Casimir effect. When you put two metal plates incredibly close together in a vacuum, they get pushed together by the quantum foam itself. It's as if space is constantly creating and destroying tiny amounts of energy, and we can detect the pressure it creates. But here's the mind-blowing part. This quantum foam existed before the Big Bang. While everything else about our universe supposedly began 13.88 billion years ago. The quantum foam has been there all along, bubbling away in the deepest foundation of reality. Scientists think this foam might hold the key to understanding what triggered the Big Bang. Maybe our universe emerged from a particularly large fluctuation in this quantum sea. Think of it like a soap bubble forming in a bathtub full of foam, except the bubble became an entire cosmos. The math suggests that in the quantum foam, time itself becomes uncertain. Past and future can get mixed up. Cause and effect break down. Events can happen before their causes. It's a realm where the normal flow of time that we experience every day simply doesn't apply. This means that whatever came before the Big Bang might not have happened before it in any way we can understand. The quantum foam exists outside of time, as we know it, in a realm where before and after are meaningless concepts. But if the universe emerged from quantum fluctuations, something had to trigger the massive expansion we call cosmic inflation. Something extraordinary happened in the first tiny fraction of a second after the Big Bang. The universe expanded faster than the speed of light itself. This cosmic inflation solved many puzzles about why our universe looks the way it does today. But it created an even bigger mystery. What could possibly have triggered such an explosive expansion? The answer might lie in a hidden phase of cosmic evolution that happened before our Big Bang even began. Picture a balloon being inflated, but instead of growing steadily, it suddenly explodes from the size of a marble to the size of a basketball in less time than it takes light to cross a single atom. That's what cosmic inflation did to space itself. In just 10 to the 36 seconds, a region smaller than a proton expanded to the size of a grapefruit. This isn't just fast expansion. This is space itself stretching so rapidly that 2 points that were close enough to touch became separated by millions of miles instantly. The expansion was so violent that it would have torn apart any matter that existed, leaving only the pure energy that would later cool and condense into the first particles. But here's what puzzles scientists. Inflation requires a special kind of energy field called the inflaton field. This field had to be perfectly balanced on a cosmic tightrope. Too little energy and inflation never starts. Too much and it never stops. The conditions had to be just right, like balancing a pencil on its tip. What could have set up these precise conditions? Recent theories suggest that our inflationary period might have been just one episode in a much longer cosmic drama. Before our inflation began, space might have been going through cycles of expansion and contraction. Each cycle fine-tuning the conditions until inflation finally triggered. Think of it like a mountain climber who has to traverse multiple peaks before reaching the summit. Each peak represents a different phase of cosmic evolution. And our Big Bang inflation was just the final summit in a long journey that started much earlier. Advanced computer simulations show that these pre-inflationary phases could have lasted for incredible amounts of time. We're talking about epochs that make the 13.8 billion age of our universe look like a brief moment. During these phases, space could have been experimenting with different configurations, different energy densities, different physical laws. The most exciting part is that some of these pre-inflationary conditions might have left signatures that we can actually detect. Gravitational waves from these ancient epochs could still be rippling through space today, carrying information about cosmic events that happened before our universe even began inflating. Scientists are building increasingly sensitive detectors to search for these primordial gravitational waves. If they find them, it would be like discovering a message in a bottle from before the beginning of time. But cosmic inflation might be just one way that universes can begin. Some theories suggest that the Big Bang was actually the end result of a cosmic collision that had been building for eons? What if the Big Bang wasn't a beginning, but a bounce? Scientists are discovering that our universe might be caught in an eternal cycle of expansion and contraction, where each Big Bang is actually the rebound from a previous cosmic collapse. Imagine a cosmic heartbeat that's been pulsing for eternity. Our universe expands for billions of years, reaches a maximum size, then starts contracting back down until it squeezes into an incredibly dense state. But instead of collapsing into a singularity, something remarkable happens. The universe bounces back, triggering what we call the Big Bang, and starting the cycle all over again. This cyclic model solves one of the biggest problems with the traditional Big Bang theory. Instead of everything beginning from an impossible singularity, each cycle smooths out the wrinkles from the previous one. Think of it like a cosmic washing machine that cleans and resets the universe every few trillion years. The evidence for this comes from studying the cosmic microwave background radiation, the afterglow of the Big Bang that still fills all of space today. When scientists map this radiation in incredible detail, they find patterns that are almost too perfect to be explained by a single Big Bang event. The temperature variations are so precisely calibrated that it's like finding a perfectly shuffled deck of cards. But in a cyclic universe, this makes perfect sense. Each cycle acts like a cosmic filter, removing irregularities and creating the smooth, uniform conditions we observe today. Over countless cycles, the universe has had time to work out all the kinks and achieve the nearly perfect balance we see around us. The math behind this is mind-bending. During the contraction phase, time itself starts running backwards from our perspective. Events that seem to happen in sequence during our expansion phase actually happened in reverse order during the previous contraction. It's as if the universe is playing the same cosmic movie forwards and backwards for all eternity. Recent observations of distant supernovas suggest that the expansion of our universe is actually accelerating, driven by something called dark energy. But in the cyclic model, this acceleration is temporary. Eventually, dark energy will weaken and gravity will take over, starting the next contraction phase. The timeline is staggering. Each complete cycle takes about 1 trillion years. We are currently about 14 billion years into the expansion phase, which means we have roughly 986 billion years to go before the universe starts contracting again. What's even more incredible is that information from previous cycles might survive the bounce. Some researchers think that complex structures like black holes or even patterns of matter could make it through the transition, carrying traces of ancient universes into our current cosmic era. If this theory is correct, then what we call the Big Bang was actually a cosmic collision between our contracting universe and something else entirely. Picture two vast sheets of spacetime hurtling toward each other through a higher dimension that we can't see. When they collide, the impact creates our entire universe in a cosmic crash that makes the Big Bang look gentle. This is the apophis scenario, named after the ancient Greek word for conflagration. Instead of our universe beginning from a single point, it emerged from the collision between two three-dimensional spaces called branes, moving through a higher dimensional realm that exists beyond our everyday experience. Think of it like two enormous soap bubbles floating toward each other in a bathtub. When they touch, they don't just merge smoothly. They create ripples, waves, and disturbances that spread throughout both bubbles. Except in this case, the bubbles are entire universes, and the ripples become the matter and energy that fill all of space. The beauty of this model is that it explains why our universe is so remarkably flat and uniform. When the two branes collided, the impact smoothed out any irregularities that existed before, creating the nearly perfect cosmic conditions we observe today. It's like two rough wooden boards being pressed together so hard that both surfaces become perfectly smooth. But here's where it gets really strange. These colliding branes exist in what physicists call the bulk, a higher dimensional space that contains multiple universes like bubbles in champagne. Our entire reality, everything we can see and touch and measure, is confined to the surface of one of these branes. We're essentially living in a three-dimensional slice of a much larger cosmic structure. The collision happened about 13.88 billion years ago, which explains why that's the age of our observable universe. But the brains themselves could be infinitely old, drifting through the bulk for eternity until the moment of impact that created our cosmic home. Scientists think they might be able to detect evidence of this collision by studying gravitational waves, ripples in space-time itself that travel at the speed of light. The impact between two brains would have created massive gravitational wave signatures that should still be detectable today, like echoes from the most powerful explosion in cosmic history. What's even more mind-bending is that the collision might not have been random. Some versions of the epiotic theory suggest that the brains are attracted to each other by forces operating in the higher dimensional bulk. They're destined to collide repeatedly, creating universe after universe in an endless series of cosmic crashes.